actually activates the respiratory system that is based on chemoreceptors. And then the transport of oxygen is either by simple diffusion, but this is only 2% of how oxygen is transported. Oxygen is actually carried by hemoglobin as oxyhemoglobin. I always write it like that. I know it's wrong. I probably should do that. As oxyhemoglobin, and this is 98% of how our oxygen is transported. And in mentioning hemoglobin, obviously hemoglobin is found in red blood cells. It sits in the red blood cell, and it can carry up to 4 oxygen molecules. It has binding sites for up to 4 oxygen molecules. So we end up really with 8 oxygen molecules being transported each time. And if we were to go back to gaseous exchange, you know, as we lose carbon dioxide, we gain oxygen, and vice versa. As we gain oxygen in the tissues, we lose carbon dioxide. So this is lung tissue. We lose CO2. So if we were to, you know, to just fit in hemoglobin, really, because hemoglobin sort of will work in the capillary, inside the capillary, it will work as an exchange mechanism, really. So if we were to think of this as a capillary, you know, either around the tissue or around the alveolar, and it has hemoglobin there. So say if this is the tissue, I'll just draw 2 oxygens really just to make a point. That oxygen diffuses into the tissue, and we have empty, well, not empty, but you know, a hemoglobin that's not carrying anything. So all it does really is just its binding ability for carbon dioxide increases, so then it actually binds carbon dioxide and carbonamine hemoglobin, and then transport carbon dioxide. So I just really wanted to show the relationship of carbon dioxide. This is a red blood cell, although it's written in green. So this is how hemoglobin fits in into the transport of both oxygen and carbon dioxide. But obviously for carbon dioxide, this is not a very efficient system, because as I've already said, the most efficient system for carbon dioxide is via the bicarbonate ions, which is found in the plasma. So in this part of the respiratory system and respiratory medicine, I have just discussed pulmonary respiration, how air is taken into the nose and into the lungs. And then I've also moved into gaseous exchange and explained exactly what happens in the alveolar and in the capillaries, and in turn also talked about what happens in the tissues and how all the gases are transported. I have also briefly touched on the respiratory centers and what actually activates the respiratory centers in terms of things like baroreceptors, which are in the carotids and aortic arc, the chemoreceptors, the stretch receptors, which are actually found in the lungs and the alveoli themselves, and the muscle receptors as well, which are obviously activated in terms of increased metabolic needs. What I haven't really talked about are things like the cough, the cough reflex, which again is similar to all the other reflexes in terms of say inhaling, I want to say dust particles, say one inhales dust particles, they irritate the respiratory tract. Irritation of the respiratory tract also activates the respiratory center via the cranial nerve 9 and 10, which I've already explained. And all it does is actually increases the force of expiration. So if you were to think about a coughing starts with a deep inhalation. So you inhale really, really deep. And then you exhale really, really deep in order to actually expel whatever, irritant has been inhaled. So again, that is based on the activation of the inspiratory centers and the expiratory centers. What I haven't mentioned, which I should mention now, the accessory muscles of respiration, and these are obviously the normal muscles for respiration. I'll just write the normal are the interthoracic muscles, which were found in between the ribs and the diaphragm itself. So these are normal muscles for respiration. However, the accessory muscles for respiration, which are usually used by people with asthma, people like me, and people with things like COPD, these muscles include the stenomastoid, or the S muscle, which arises from the manubrium of the sternum. It's actually located. So this is the sternocleidomastoid. I don't know why I wrote it like that. It's the sternocleidomastoid muscle. So the sternocleidomastoid muscle arises from the clavicle, as we say. Obviously, that's the first rib, like from the clavicle and the manubrium of the sternum. So it attaches there. And it's a muscle that runs across our neck there. So from being there, it then attaches onto the mystoid of the temporal bone in the heart. So because it does that, I'll show it on myself because drawing it will take forever. So it attaches there and descends through the neck in a I'll say no, not horizontal, more a bit oblique to attach into the clavicle and the manubrium of the sternum, hence its name, sternocleidomastoid muscle. The other accessory muscles are the scalene muscles, and these are the anterior vertebral muscles. And all that it means is that they run parallel to the cervical and thoracic vertebral bones. So they just run parallel to around the neck area. I can't remember what C it is, and I don't want to say it in case I say it wrong, but these are the two accessory muscles that are that are normally used in people with pathologies like asthma, when they have to breathe really, really deeply during an asthma attack, and COPD. So these muscles get activated, and they are under accessory nerve, under the accessory nerve. Again, the other muscles that are activated again in terms of the other accessory muscles, I'll say the secondary ones, are the abdominal ones. So in terms of muscles and in terms of the compromise in breathing, because we have obviously a lot of muscles, our breathing is controlled by a lot of muscles. So we do have to consider things like neuronal diseases, what can compromise breathing, like neuronal diseases such as, for the life of me, I cannot think of a neuronal disease. Any disease that's muscle wasting. I want to say Guillain-Barré syndrome, or the skeletal diseases like muscle wasting. Things like MS, anything really that causes muscle wasting, and skeletal diseases such as kyphosis, scoliosis, and muscular diseases themselves. The neuronal and muscular diseases they more or less relate and overlap in terms of obviously muscle activity has to have neuronal innervation. So when we think about breathing, we don't just think about diseases which affect the respiratory system like asthma and COPD, but we must also consider things that affect the muscles, because a lot of other pathologies will come from that as well. Because imagine if someone say had a neuronal disease and they couldn't cough up anything that enters their lungs, so that's someone who's just prone to constant infections. Again, the other thing which I forgot when I was talking about this is just filling in the blanks as I remember. Alveolar. Also has macrophages. The alveolar also has macrophages, which is obviously the first line of defense. But the important thing, the reason why I'm just quickly mentioning macrophages in the alveolar is obviously because if we remember, macrophages, what they do is they will engulf whatever foreign object or foreign body is that has invaded the respiratory system. But what they do is stimulate inflammation. So now we're not talking about macrophages that are found, say, in the upper airways. We're actually talking about macrophages that are found in the smaller airways, in the alveolar itself. So we're talking about macrophages that are found, at the actual terminal of the airways, the smaller airways. So any inflammation that happens, say in the alveolar sac or in the terminal bronchioles, will eventually cause things like fibrosis. For example, if someone has active bronchitis that does not go away because they are smoking, they will end up with a fibrosed bronchiole. And as it fibroses, it narrows and becomes less elastic. Remember, the bronchioles have smooth muscles and elastin. So that if there is continuous chronic inflammation, we end up with things like fibrosis. And if that chronic continuous inflammation happens in the alveolar, because obviously the alveolar has resident macrophages, we'll end up with things like bronchiectasis, where the diameter of the bronchiole actually increases like that, and all the ridges that allow for an increase in surface area and elasticity are destroyed. We'll also have obviously fibrosis as inflammation continues forever and ever and becomes chronic. But the increase in diameter of that alveolar means that gaseous exchange is poor, and it cannot happen because remember, gaseous exchange is based on pressures. So now diseases that are found, in terms of the inflammatory system will be things like pulmonary fibrosis and bronchiectasis. And this is obviously much more common in people with CF. But then again, I'll cover this properly in pathology. It's just that I always think that it's much easier and it makes much better sense to, look at things that can affect areas where when one is talking about the anatomy and physiology, because then it actually relates better to pathology and makes pathology so much easier to learn. Anyway, this is the end of this lecture. In this lecture, I have covered the breathing muscles, I've covered the respiratory centers, I've covered respiration, both in terms of pulmonary respiration, internal and external respiration, and indeed the transport of gases, including gaseous exchange. I have also briefly introduced a few diseases and shown how pathology fits into the anatomy and physiology. So in the next lecture, I'll basically be talking about pathologies, starting with COPD.